Thank you for coming to our session, Moving to the Lakehouse, Fast and Efficient Ingestion with Autoloader. My name is Benyu Emma Liu. I'm a product manager at Databricks. Prior to Databricks, I worked as a product manager at TigerGraph and MarkLogic, also as a software engineer at Oracle. My domain focus is on cloud computing, database as service, multi-model and graph databases, developer DBA tools, and containerization. My co-presenter today is Eric Maynard. Eric will introduce himself.
And I'm Eric. I'm an engineer at Databricks, working on data ingestion. Prior to that, I was at Instagram, and my focus at Databricks has primarily been on streaming, optimizing streams, and making Autoloader scalable and easy to use.
Thanks, Eric. Let's take a look at our agenda today. First, we're going to talk about Databricks Lakehouse overview, and then we'll have a high-level overview on Autoloader. Then we'll discuss a few typical customer use cases for Autoloader. And Eric will take us into a deep dive on Autoloader and provide a demo at the end. Before thinking about ingestion into Lakehouse, we should understand why ingesting into Delta Lake is the right solution in the first place. Let's have a quick look at the Databricks Lakehouse architecture. The Lakehouse architecture unifies data lake and data warehouse and is built on top of Delta Lake. And Delta Lake is an open, reliable, performant, and secure data storage and management layer for your data lake that enables you to create a true single source of truth. Since it is built upon Apache Spark and the new Photon engine, you're able to build high-performance data pipelines to clean your data from raw ingestion to business-level aggregates, and of course, machine learning training and model serving. And given that it is an open format, it allows you to really avoid unnecessary replication and proprietary locking. Ultimately, it provides the data quality, reliability, performance, security, and governance you need to serve your downstream data use cases. Really, the Lakehouse, your single source of truth for your data built on top of common security governance model, enables you also for multi-model collaboration in one single platform. You can use open APIs and standards for all your data engineering, data warehouse, streaming, and data science and ML needs. This is why Databricks is the data and AI company with the Lakehouse architecture. No one else can do what we can with a single solution. Now let's take a look at Autoloader, our recommended native tool to ingest files from cloud storage to Delta Lake. Ingesting and querying structured, semi-structured, and unstructured data can be very tedious and time-consuming, but Autoloader and Delta Lake make it really easy. Autoloader can actually listen to new files arriving and ingest when files arrive. A quick intro to Autoloader. It is available in Python and Scala, and it caters to incremental data loading use case and guarantees exactly once ingestion. It is performant, optimized, and scalable for large amounts of data, and is designed for structured, semi-structured, and unstructured data. We actually have a webinar series that's on hassle-free data ingestion for all these three different types of data structure. Autoloader can discover files in two different modes, directory listing and file notification mode. Directory listing is the default mode, and it's super easy to get started. For directory listing, optimization has been done further to make it cheaper to ingest partitioned files and auto-detects lexical ordering. If you use file notification mode, it automatically sets up file notifications given the permissions and could process millions of files an hour and it usually is used in the case that files are being uploaded arbitrarily at different times. Let's take a look at all the benefits from Autoloader. It's super simple, not much logic required from you to discover what files are new. It provides the data quality for the ingestion process. It handles late data automatically and handles schema evolution for the arriving data. And it's very performant for discovering the files. And of course, it's scalable, and there are customers ingesting trillions of files with the Autoloader. And it's very cost efficient because of the efficient file discovery. I want to mention again that we have a webinar series already available on Databricks website. It's called Hassle-Free Data Ingestion Webinar Series. And you can find it in the link below. And there are 3 parts to it, which handles the overview, semi-structured data, as well as unstructured data. Really encourage you to take a look at these webinar series. I also want to mention a few other related ingestion sessions during the Data AI Summit 2022. First one is a live session, Hassle-Free Data Ingestion into Delta Lake. Make data ingestion simpler. That is actually a live session, and Brock and I will present. A second one is Ingest Data into Lakehouse with Copy Into, where my colleague Yao Hua and Jackie will present. It is a virtual session. Now let's take a look at a few typical customer use cases that Autoloader can enable. There are many use cases and variation where Autoloader can help you to ingest data to Delta. But here, we're just going to take a look at a few of them. Use case 1, customer asks, hey, my company uses an on-prem OLTP database, and we want to migrate the data to Delta Lake in AWS. How do we do that? The answer is you can use Autoloader and first move the on-prem database to AWS 3 and use Autoloader ingest into Delta Lake. Of course, similarly, you can leverage Azure or Google Cloud equivalent object storage if you choose to be on the other 2 clouds. Autoloader and Databricks are available in all 3 clouds. A second use case, customer asks, hey, we have upstream applications writing data as files to ADLS, S3, or GCS, and want to load these files every night at 9 p.m. to Delta Lake so that we can refresh reporting dashboard every day. And the upstream application may occasionally change schema of the file. And yes, the solution is Autoloader. You can actually have the applications writing using a message bus of your choice and ingest into the Cloud Object Store as files. And then you trigger Autoloader as at a schedule using workflow. And this accomplishes a scheduled ingestion to Delta Lake. And the third use case, our customer asks, we have devices sending images to AWS S3 or Azure ADLS, GCS every 5 to 10 seconds. And we need to ingest images to Delta Lake and run object detection on the images using machine learning models so that we can return the information to our users. How do we do this? And yes, the solution is you can use Autoloader and use the file notification mode, which can help you to achieve the continuous image ingestion to Delta Lake. There are many, many use cases that Autoloader can help you ingest data to Delta Lake. There are many formats that Autoloader support. For example, CSV, JSON, Avro, Parquet, binary text, ORC. And there are many ways of ingesting, for example, continuous, scheduled, and also everything is incremental ingestion with Autoloader to Delta Lake. I encourage you to check out the documentation for many of these details and variations. And now Eric is actually going to take you into a deep dive of Autoloader and investigate some of the newer features that we added, and also provide a demo.
Now we're going to deep dive into Autoloader and talk a bit about some advanced features. The first thing that I want to talk about are these two ways that Autoloader can discover files. So the first one that you're likely to use if you're testing Autoloader is directory listing mode. And this does what it sounds like. It repeatedly lists the input directory and discovers any files that haven't been processed, processes them, and labels them as having been processed. It's simple to set up, works well for small throughputs, and we have optimized cloud APIs that reduce RPC costs. So when you compare this to just listing the bucket in Spark, or even just reading the bucket through a data frame, reading Parquet data, for example, Autoloader will still reduce the RPCs. Now, if you have a little more throughput, or you want to reduce those costs further, you can also enable file notification mode. And file notifications allow scaling to millions of files per hour, but they require you to set up permissions. There's also one more case here that I want to talk about before we talk in more detail about what we've already discussed, which is incremental listing mode. So incremental listing mode is kind of a special case of directory listing where the files are arriving over time in an order that is also ordered by the file name. So there's some example files here, but this is actually very common when files have like a timestamp prefix. And if you have this ordering, you're able to use incremental listing. And as you can see on this little graph on the left here, incremental listing performs pretty much just as well as file notifications, perhaps even a little faster on some clouds, but it's able to scale beyond what file notifications are able to scale to. With file notifications, at some point, you hit these scalability limits of the cloud queue itself, of SQS, of PubSub, et cetera. So you can see that directory listing performs quite well. And in fact, it's pretty much the same as file notifications for relatively small throughputs, 10,000, maybe 100,000 files per hour. But as you get into the million files plus per hour territory, directory listing can really start to slow down. One more quick note here. There is a feature in Autoloader called native listing. So Autoloader has this native listing I talked about that skips the Spark file system API and uses cloud native APIs to list the whole directory on the driver without creating tasks for the executors. This means that each list of the directory is just one API call instead of one per directory. So for some nested directory structures previously, if you just use Spark without Autoloader to read these directories, you may see thousands or even millions of calls to the cloud object store. In rare circumstances, though, it's worth calling out here, this can degrade listing performance. Because all the work is being done on the driver, for very, very large directories, you may see that disabling native listing actually yields better performance. And the SQL configuration that controls this is called out on this slide. Most of the time, you don't need to do this. But again, if the directory is truly massive, you could consider disabling this. So let's talk in more detail about incremental listing. Incremental listing will automatically detect when it can work. So you don't need to know, hey, my files are arriving in this order and I'm going to turn it on. It'll automatically detect when files are arriving in a sorted order. There is this configuration here, which is set per stream, which can be set to true to forcibly enable incremental listing, false to disable it, or the default, which is auto to detect it in the way that I mentioned. There's also a periodic asynchronous backfill, which will scan the entire directory. This confuses some folks because they understand that they have incremental listing turned on and they see this full list. But the reason that this is on is just to catch those straggler files that may arrive outside of sorted order. If 95 or 99% of your files are arriving in sorted order, it's probably still wise to have incremental listing on. It'll save you a lot of costs. It'll reduce latency greatly. And this asynchronous backfill that happens in the background will catch any files that slip through. This has a backfill frequency, which is controlled by the argument given here. And as I said, incremental listing only lists the new files. It starts the list using those cloud native APIs I mentioned. It starts the list from the most recently discovered file, or a little bit before it actually, which will dramatically improve cost, dramatically improve latency, because you're not listing a million files, you are only listing the new ones. So I think it might be useful to compare directory listing mode and file notification mode, the two file discovery modes for Autoloader. One thing that I want to clear up is that both are only processing new files. There's no difference there. The function of Autoloader is fundamentally to discover new files and process them. Directory listing mode, I will say, is easier to set up. It doesn't require any additional permissions or anything like that, and it is the default. File notification mode, on the other hand, can support more complex paths. You can add custom filters, custom rules to the cloud event subscription on your cloud provider. It is cloud dependent though, so which filters are available or not available will vary depending on the cloud you're using. Directory listing mode, of course, does incur some overhead due to that list that's happening. There, you will see that getting those batches, if you were to examine the logs, getting those batches does take more time. It has to go out and actually do the list. I will mention also that file notifications are specifically more efficient for globs. On some clouds, we have some additional filters we apply if your path is really globbed or deeply nested. So with directory listing mode, you're always listing from the top level directory and you have to list down inside all those directories, whereas file notifications tend to not have that drawback. And of course, in directory listing mode, you also have to rely on a synchronous backfill to ingest everything, even in incremental listing mode, right? There's going to be this full list that's always happening. That's one major drawback in order to get completeness, I'll say. Now, in file notification mode, you could be subject to those cloud queue provider account level, maybe queue level restrictions. You will start to see those throughput limits. And that's why in the chart we looked at earlier, eventually, in incremental listing will sort of outscale file notification mode, but only at very, very large throughputs. So in conclusion, right, directory listing mode, very easy to set up, works well for most users, works well for most data volumes. As the input directory grows larger, it will slow down. So deleting files that have been ingested is something that's really wise to do. You can consider also cloudfiles.clean source, a new option that we're rolling out in DBR11 that will automatically archive some of these files for you. File notification mode, on the other hand, is really scalable. It's not limited by the size of the input directory, and it can ingest millions of files per hour. Depending on the cloud, it could be tens of millions of files per hour. If your data does arrive in a sorted order, incremental listing could outperform even file notification mode for those really massive input volumes. All right, we're going to change topics here and talk a bit about schema inference. So one problem that real streams often encounter is disparate data, right? You have one source that's providing data. Here it's going to be JSON data in a given format with the fields foobar. And another source is only providing one of those fields. Or maybe it's providing one of those fields in some other third field. Or maybe it's providing it and it's a different type, etc. So Autoloader can first infer the input schema from a sampled input file. So it'll look at not necessarily all the files, but several of the input files, and this is configurable, to figure out what the overarching schema that is common across all these files, the superset of fields, that it can use to define the stream, which ultimately can be written to your target table. And this inference only happens on the first run. You can also skip it if you manually provide a schema, but if you don't and you rely on schema inference, this will be persisted in the checkpoint or in the schema location after the first run. You can provide a schema location through the options. Now, what happens when the schema changes? So you've done schema inference and you've inferred some schema, but the sources start writing data with a new schema. This happens a lot in real life, right? So Autoloader fundamentally, what it's doing is it's monitoring some directory, and you can drop any file into that directory. So what happens when some file shows up that does not align with the schema that Autoloader has expected for this input directory? And I think it's easy to say like, oh, well, we should ignore it, or we should just add it to the schema, but there's not always one clear answer here, right? It's going to depend on the stream. It's going to depend on the business needs, right? Why does the stream exist? What quality of data do we expect the stream to produce, et cetera? So it could be a new field. It could be a legitimate new field that we should add to the stream, but it could also be a mistake, right? Someone could be running maybe the wrong version of code. They might have produced some bad data. Who knows, right? So Autoloader provides several different options for dealing with these new fields. One is to add the new column. So if the schema has been persisted and some data arrives that does not align with that schema, we can simply add new columns that have appeared. We can also fail on new columns, right? If we really expect this data to be strictly adhering to the schema that we've defined, we can fail on those new columns. We can also ignore them. If we only want the columns that we've called out, and we know that sometimes maybe erroneous data will show up, we can just ignore it. We can also rescue it. So this is sort of a point of confusion for some folks. What does it mean to rescue this column? So Autoloader can rescue data that doesn't conform to the schema. There is something called a rescue data column, which is underscore rescue data, as you can see in the Delta table there, which encodes all of the rescue data, all of the data that didn't align with the schema, all these extra columns in JSON. So here you can see that the first two files have the fields foo and baz, and that might have been defined as the schema. And as you see here in Delta, we have the same columns. And then eventually this third source shows up and it produces data with this column bar. And we don't want to add it. We don't want to ignore it. We don't want the stream to fail. So what we do is we rescue this column bar, and you can see in Delta, you'll see a column called rescue data, which is a JSON with all of these fields. If there are multiple fields, they would all be there. One important call out is this is, a string JSON. So if the field was maybe an integer that showed up here, or it could be a Boolean, right? It's still going to be encoded as a string here. So once data has been written to the rescue data column, how do we cease rescuing that data? How do we deal with it downstream of Autoloader? So the important thing to know is that Autoloader is persistent at schema, like I mentioned, into the schema location. And if we explicitly provide a schema to the stream, it'll override whatever's been written there. So if we don't want to rescue a column anymore, and we want to kind of promote it to be a real column, we can simply add it to that schema. Now, this will not affect existing data. The existing data in Delta Lake will not have that column populated. It'll be null, and the rescue data field will still be there. But data going forward will treat this column as a real column. It'll be populated in Delta Lake. It will not go into the rescue data column. So what can we do to get the data that's stuck in that rescue data column out of there and into this real column that we've now decided as part of the schema? So the simplest thing that you can do is in a downstream pipeline, you can just treat it like any normal JSON column. You can extract it in accordance with business logic. Here you can see I'm just using the semi-structured operator here, rescue data : bar. You could alias that back to bar and treat it just like a real column. If you have modified the schema and you now have this real column bar, and you also have rescue data and maybe some of the older data, you can coalesce these things together. So you can say coalesce bar with the rescue data bar field as bar. And now you have one column that appears to downstream consumers who have always been populated the whole time, even though for a time, it wasn't clear whether this was really part of the schema, it was being rescued, it was showing up in the rescue data column. So we have seamless sort of continuity of the schema as it evolved. So in summary, right, real data, real streams are unpredictable, and you don't know whether new data should be included, should be dropped, should fail the stream, etc. And Autoloader's rescue data feature gives you flexibility to deal with it in whatever way you see fit downstream of your Autoloader stream. As I said, right, you can either update the stream, which will start populating it from that point forward, or you can go back and you can extract it from the rescue data column in some sort of downstream pipeline. You can also do both, as we saw in that example. I should mention that you want to type things properly. I probably don't have to mention this, but if it's an integer, it should be typed as an integer. And so getting it out of that rescue data column will allow your pipeline to be a little more efficient, both in terms of storage and also if you're, for example, querying it, having to extract it out of a JSON every time and cast it to integer does incur a cost. And as I mentioned previously, right, we also support just adding the column, dropping the column, or failing. Cool. So one more topic I want to discuss is how do you monitor the state of an ongoing Autoloader stream, right? Autoloader fundamentally is providing exactly one semantics. How do I know which files have been processed? Especially in the context of, for example, directory listing mode, where you may want to delete files after they've been processed to keep the size of that directory small. How do I know which files have been processed? So we're going to talk a bit about a new function added in DBR11 cloud file state. So in order to provide that exactly once guarantee that I mentioned, Autoloader streams are stateful. They store the state of the stream in the Spark streaming checkpoint, where information about each individual file is recorded, the size of the file, the name of the file, etc. The state of this checkpoint can be analyzed with the Spark SQL function cloud file state. The cloud file state schema looks like this. So you provide the checkpoint that the stream is associated with to the function, and you will get back the path of each file that Autoloader has seen, discovered, the size of the file, the time at which the file is believed to have been created. This is either based on inspecting the actual file itself in listing mode, or in file notification mode, it is the event time associated with the event that notified Autoloader of the file's creation. Also the delete time if the file was deleted, the discovery time, which is the time at which Autoloader did the list or did the encountered the file notification that actually notified it about the file. the commit time, which is when Autoloader committed that file to the checkpoint and actually finished processing it, and also the archive time. If you're choosing to use Cloud Files clean source, that would be the time at which the file was deleted or otherwise archived. I will mention also there is a SQL config which is required to enable the commit time monitoring. It's called out on the slide. There's a small cost associated with this. We're still rolling it out, but if you'd like to enable this feature, you can enable it with the flag on this slide. Another important call out is that eventually old files, let's say files that were discovered a year ago, will be cleared out of the Autoloader state in accordance with cloud files.max file age. That is the max file age we expect to have to ingest. This age being relative to the stream time. So if max file age is 14 days, that means that we don't expect a stream to run one day and have to process data from 15 days ago. And if max file age is set, what happens is Autoloader will go through and eventually delete these records from its internal state. So this is an example query using the cloud file state TVF. Each file is tracked, as I said, until max file age expires. So you can query some individual file if it has some path. For example, here, plant 42, if you want to see all the files from plant 42, when they were created, you can do so like this, right? And of course, we can take this commit time and treat its lack of being null as an indicator that the file's been ingested, only if, of course, the flag I mentioned on the previous slide is set. Oh, and I mentioned this here, I should have called it out sooner. The grain of the table is path. That is, path is unique in this table. So you won't see two records that have the same path, and each file should have exactly one record associated with it. You can also measure latency using this function, right? So by comparing the commit time, which is the time at which Autoloader finished processing some file, and the create time, which is the time at which the file was created, we can sort of approximate the latency of the overall stream. I also want to talk about discovery time here. I know I mentioned this previously, but this is when Autoloader first discovers the file after it was first created. So if you're really looking at the latency of the stream itself, it may make more sense to look at discovery or create time, depending how you want to define latency. But discovery time is when Autoloader had the opportunity to begin processing the file, and commit time is when it finished processing the file. If you were to run your stream more frequently, you should see the gap between create time and discovery time sort of shrink. So in summary, for monitoring a stream, cloud file state exposes the internal state of Autoloader for querying using the fields that we talked about before. The state can be pretty big. It's not small. We're tracking every file you've ever seen, but it does provide the exact file level information that Autoloader is internally using. I mentioned this also, but commit time tracking incurs some overhead. There's a SQL conf. It's false by default. Here it is again. And commit time is really the only surefire way to know which files in the input directory have been fully processed by Autoloader. So you can kind of assume that really old files have been processed. And I think this is what a lot of folks do with lifecycle policies, et cetera. But if you want to know for sure whether or not a file has been processed, you can look at commit time. So we talked about the frequency at which you run your stream. And I also want to briefly talk here about running streams, running Autoloader streams. So Autoloader streams are kind of interesting when you think about it, because you're taking batch data that's dropped into this directory in batches, and then you're creating a stream through Spark structured streaming, but you may not be running a continuous stream. You may be running Autoloader jobs, for example, hourly. So you kind of have this batch data, which is becoming a stream only once every hour, which sounds a lot like a batch. So it's taking these discrete files, like I mentioned, turning it into a stream. And there are several triggers available to the Autoloader stream and also to all Spark structured streams. So one is continuous, which just means run it as fast as you can. Processing time, probably the most common stream trigger that we see. Trigger once and trigger available now. These are the two that we're going to talk a bit more about. So these modes process all the data currently available and then terminate the stream, right? So if you do trigger once, you're saying, I only want to run one batch. I want to take all the data that's in the directory right now that I haven't processed previously, that is, process it, and then terminate the stream. So trigger once and trigger available now. Trigger once runs one large batch for all the available data. Pretty straightforward. You take all the data that's in the directory that hasn't been processed previously, process it in one big batch, and then terminate the stream. Trigger available now semantically does the same thing, right? It looks at what data is available when the stream starts, and then runs as many batches as it needs, which could be one, could be more, in order to process all of that data. Trigger available now also supports max bytes per trigger, max files per trigger to limit the amount of data that's processed in each batch. And it tends to be more scalable because it doesn't have that limitation, that implementation detail really of running just one batch. And so with these triggers, Autoloader can be scheduled to run either on a regular basis or just use ad hoc as needed. You can see here, schedule UI. So now we're going to go through a demo where we create an Autoloader stream and look at some of these features we've discussed in more detail. Okay, cool. So now we're going to look at a real Autoloader stream and play with some of the features that we just discussed. For starters here, we're going to simulate a application that's generating data for Autoloader. So what we'll first do is just define some functions, and we're going to be generating data in this JSON format. So there's 3 fields, there's an ID, a name, and a balance. And so we'll start generating data in this format in our input directory here. And every 2 seconds, we should see hopefully a batch of files. Yep, there's 3, 6, etc. Cool. So with this fake application running, let's go and start up our Autoloader stream. So first, let me just make sure I clear out any existing stuff in here. And here we'll start a stream with trigger available now. So what this means is that the stream isn't going to run continuously. It's going to run not one batch really, but run once, process everything in the directory, and then finish. We've specified the format as JSON. We've provided a schema location and a checkpoint location. And we're going to write to this table, which is the Data NAI Summit 2022 demo. So go ahead, kick this off. Should take a little bit for the first time setup. We can see here, schema inference just happened. It mentioned a sample of 49 files. And once this finishes writing to Delta, which should hopefully be soon, we can go ahead and look at the output in this table here. Looks like the actual job is running, so it's processing the files now. And it just finished. Great. So let's see what schema we got. Sure enough, we see those fields that we specified in the JSON: balance, ID, and name, as well as the rescue data column. One thing that's important to note here is that unlike other Spark streaming sources, JSON schema inference does not infer data types by default. This is configurable, but Autoloader will by default just make everything a string type. This is really to avoid headaches with columns getting nulled out and things like that. But this is behavior that you can restore to the same as the other data sources if you'd like. So now that we have the schema, let's see what's actually in here. And again, no surprises here, right? We see the balance, the ID, the name, and that null rescue data column. So what's going on in that rescue data column, right? Why is it always null? Well, because the data that's coming in, these JSONs, right? They conform to the schema, which was initially inferred, right? The data hasn't changed in a sense. Now, because we ran that in trigger once, we can count this table, for example, as many times as we like. There's 610 records, 610, that's not going to change. If we were to go back up and trigger this one more time, won't take quite as long this time. It doesn't have to infer the schema. It really just has to run, do the list, etc. If we go back down and we take this count one more time, there it is. We'll see that it is climbing up, right? Data's been generating this whole time in the background. So every time we trigger the stream, more data gets processed. What happens if the data starts coming in a new schema, right? So if we stop this, we redefine this function to add another field, the det field, which is an int. What's going to happen to our stream? So we redefine that, we kick off our fake data generation application, and we return here. We're going to run our stream one more time in available now mode, but this time we're going to enable schema evolution mode rescue. We don't want to add the new column, which is the default behavior. We want to rescue it. So if we do this, without having to specify the schema or change anything else, we see that the stream just sort of proceeds as normal. So what exactly does the table look like? Not just that file path, but what is rescue data like, right? So here's that JSON object with the det field here and this sort of pseudo hidden file path column. So we can see which exact input file the rescue data came from. And this is important because sometimes you have just one source sending erroneous data, or there's some pattern where certain files are showing up, and this can help identify that. So what if we want to promote this column not to be rescued, but to actually be part of the schema? So now we're going to add 2 configs. One is merge schema, which will allow the Autoloader stream to actually update the output delta table schema. And the other is the schema. We're going to use the DDL syntax here, but the schema option. So here we just provide the det column here. We're specifying that it's a big int. even though it's a string here inside the rescue data column, and the other columns, which you'll remember were all strings. So if we run this, so when we query this now, we can see that sometimes this det column is getting populated. There's a big int here because we've promoted this to be a part of our schema. Now the rescue data is back to being null. There's no columns being rescued. But I think if we scroll around this output, so we can see there's sort of this either or behavior, right? The column is either getting rescued or it's part of the schema. And so in order to rectify this, we can coalesce it, as we discussed before, right? We can coalesce the det column, which is populated, with the extracted det value from the rescue data column. And here we're creating a view out of that. So we'll let that run. And when we select from our view, we can see that this det column is always being populated now, right? So we've taken the rescue data, we've coalesced it with the actual data, and now we have a consistent view as if the schema was always the same all along, and as if this column always existed all along. One more thing to check out too is that we can inspect the state of this running stream. And we can see whether or not, for example, the file size changed when we added this new column. You can see it's all quite uniform. And then at some point it goes from about 500 to 600. But we can see, for example, what time a given file was ingested or how long it took to go through the stream. So we've created an autoloader stream in both a trigger available now batch mode and in the normal processing time mode. We've evolved the schema of that stream as it ran, and we've inspected the state of the stream in order to learn about the files it's processed. So we've used Autoloader in both a batch and a streaming mode. We've evolved the schema of the stream as it ran, and we've inspected the state of the stream to see how it changed as the schema evolved. We've learned how to use the rescue data column and turn the rescued column into a fully promoted column in the schema. That's about it for this demo. I hope that the review of the features we discussed was helpful, and thanks.
Thank you, Eric, for the fantastic demo. Let's wrap up the session. First, we talked about Databricks Lakehouse overview, then discussed Autoloader in high level. We then talked about a few typical customer use cases. And Eric helped us to deep dive into Autoloader features and provided a wonderful demo. To learn more about ingestion and Autoloader in general, you can check out the documentation, read our ebook, and also watch the ingestion webinar series. There are 3 hassle-free data ingestion webinars already available on our website. Of course, check out the other 2 sessions related to data ingestion in our live session as well as online virtual session. Thank you. Thank you again for attending this webinar.